Hi, class. So at this point, I want to talk a little bit about organismal interactions, specifically in the plant community. And Claudio will have been talking to you about organismal interactions in arthropod communities and other types of communities. They'll be talking about trophic dynamics. But specifically, plant-plant interactions are important organismal interactions in agricultural systems. So for a minute, I just want to motivate this at a high level with this slide that walks through some critical forces that shape communities. These are organismal interactions, broadly speaking. Not all of them are relevant to plant-plant interactions. Ultimately, what I'm trying to do is get us to this competition here. So predation is a type of organismal interaction where you get consumption of one organism, the prey. The prey is being consumed by another organism, the predator. And here's an example of a lady beetle eating a soybean aphid. Parasitism is the partial consumption of an organism that is concentrated on only a few individuals during the lifetime of the parasite. And so then an example of this would be pathogens. I'll skip competition here for a minute and talk about disturbance. And disturbance is something we've talked a little bit about already with respect to the soil. But a disturbance is any abiotic or biotic process that results in a loss of biomass in a relatively discrete period. And if we're talking about the soil, we can replace the word biomass with something like soil structure or soil aggregation. We talked in earlier episodes about soil disturbance being a breaking up of the soils, and we'll see some examples of that when we talk about ways that we control weeds in agricultural systems, and particularly in organic systems. An example of disturbance is grazing. So grazing by livestock, grazing by grasshoppers, herbivory of all kinds. And then let's get to competition then, because that's the main thing that I want to talk about today. That's an interaction between individuals brought about by a shared requirement for a resource. So we've talked about nitrogen being a nutrient that's often being competed for. Water is a resource that's often being competed for. Light is a resource that can be competed for. Space is a resource that can be competed for. What happens when you get these interactions though between individuals, and it's important to note that these interactions can be within a species, which we call intra-specific competition, or between species, inter-specific competition. No matter whether it's intra or inter, it leads to a reduction in the survivorship or the growth or the reproduction of some of the competing individuals. Okay, so an agronomic example of this would be weeds, where we get inter-specific competition between a crop and plants that are not planted as crops, are not sown as crops. They're undesirable. The definition of a weed is a plant that is undesirable in the location it's in. So it's a completely a human construct, and that it relates to that plant's desirability. I want to motivate this discussion about weeds by introducing a long-term field experiment. This slide's a little dated. It says 26 years. It's actually 29 years now. The Wisconsin Integrated Cropping Systems Trial, what we call WICST, was an experiment started at the Arlington Agricultural Research Station, about 30 miles north of Madison, by Dr. Josh Posner. And Dr. Posner was an agronomist in here at UW-Madison, passed away about 7 years ago now. His last PhD student was Dr. Greg Sanford, who currently manages and runs WICST. And Janet Hedke was Josh's research technician for quite a long time, and helped Josh build and manage WICST. So WICST is unique. It's shown here in this picture as these side-by-side cropping systems that are planted on about a 60-acre patch of field. And so that's a large experiment. And each experimental unit or treatment, which are these relatively narrow and long strips. And so you can see here, this is a corn strip, and here's probably a soybean strip. There are also some native prairie strips in this experiment. You can barely make out up here, there's a managed grazing treatment as well. Every treatment is replicated 4 times. All right, and I'm about to walk through what the experiment's looking at. Just for some broader context, you can see from this aerial photo up here in this part of the world, this used to be Prairie. This is an old, this is a site that's embedded within what was once known as, I guess it currently is known as, the Empire Prairie, which is one of the biggest contiguous prairies that we had in this part of the world. Of course, most of it has been plowed under and turned into agriculture. Okay, so they established this system in 1989, and here you can see the cropping system. Originally, it was at 2 locations. One at Arlington, as I mentioned, and then there was one location down here in the southeastern part of the state called Lakeland, or in Elkhorn, Wisconsin, and it was discontinued in 2002. The Arlington experiment has continued. The plot sizes are about 3/4 of an acre. We use big agronomic scale equipment to manage them. And then they were started to look at these general performance metrics. The productivity of these systems was important, is important. The profitability, which can be very different than productivity. So we can talk about why profitability might be greater in one system and productivity greater in another system. And then the environmental response of these systems is important. And we've measured all manner of environmental responses, the carbon in the soil, the nitrogen that is lost from the systems, the amount of biodiversity in these systems, et cetera. This map is just showing current and former ag research stations in the state of Wisconsin. So let's look quickly here at the cropping systems. Here's a depiction of the WICST cropping systems, and there are 9 systems in total. 3 of them are what we call cash grain crops. That is, they're systems where you grow the crops, harvest the grain, and sell it on the market, the commodity market. There are 3 systems that are typical dairy forage systems in the state of Wisconsin. And then there are 3 systems that are native grasslands. Let's start from the bottom here with the native grasslands. We have switchgrass that was planted as a monoculture, that is, as a single crop. Switchgrass is an interesting crop that's being considered for bioenergy production. We won't talk about that today, but it also is planted quite a bit along roadsides and in prairie restorations. We have a 6 species low diversity prairie and a 25 plant species high diversity prairie. So these are plant species. And these are the numbers of species that were sown in 1989. Subsequently, these 2 prairies have kind of converged on each other in terms of their species composition, who's there, and their diversity, and what abundance are various things there. Our forage systems are what we call a conventional system, which is to say it's the kind that is conventionally used in Wisconsin. It's the typical dairy forage rotation, where we have 1 year of corn followed by 3 years of alfalfa. Alfalfa is a perennial crop that gets planted, and then that same individual plant survives, well, at least most of them do, survives and grows from year to year. And so if we didn't go back into corn in year 4 or 5 here, if we didn't go back and plant corn, this alfalfa would continue to grow for a number of years. But alfalfa does tend to decrease its productivity over time, especially after 4 or 5 years. And so we tend to break the cycle by planting corn, and then we go back into alfalfa. Now the alfalfa is a very important component of cropping systems because it is a nitrogen fixer. It's a legume. So it fixes nitrogen, brings it into the ecosystem. It gets caught up in the soil as the alfalfa turns over. The alfalfa roots die as they explore for nutrients, and that nitrogen enters into the system. And then subsequently, plants like corn that are not nitrogen fixers are able to take up that nitrogen. Okay, so the theme of our module is, should I buy organic? And so here's what we're trying to get to here, is that one of our systems is an organic corn alfalfa rotation, but it's modified a little bit in that we have, we first plant oats into the alfalfa in an effort to try to control weeds. And that's really where I'm trying to get here. In the conventional system, the conventional way of controlling weeds, which again are undesirable plants in this rotation, so not the corn or the alfalfa, but things that volunteer and colonize and try and grow among the alfalfa. The conventional method to control those weeds is with chemical interventions. So Roundup, which is a brand name for glyphosate, is sprayed in these systems to kill those weeds. Other chemicals are used as well. But the conventional part implies that the weed control happens via chemical management. As we've learned, organic systems don't allow chemical management, and so really limits the way that weeds can be controlled. And one of the ways we control it is by getting a plant that grows very quickly, very early, that is desirable, and that outcompetes weeds that are trying to get into the system. And the idea is that then once we have the system growing with alfalfa, that perennial alfalfa can block weeds from getting into the system. And but they don't completely, and so we still have to look for ways to manage that alfalfa. Okay, our cropping system 6 is this rotational managed grazing. This is perennial grassland. Here's a picture of it over here being grazed by livestock. In these two systems, the alfalfa and the corn and even the oats are harvested to be fed to livestock that are living in a confined situation. So they're pinned in a barn and really spend most of their lives in a barn, having their feed brought to them, being milked, and then having their manure and excreta either pumped out of the barn or scraped out of the barn into large lagoons. And then it's brought back out to the fields and spread on the fields when, generally speaking, when plants aren't growing. So in the fall and in the spring, when the annual crops have either been harvested or when they have not yet been planted, or right after they've been planted when we still have bare soil. So our typical conventional dairy forage rotation, we grow these crops, we feed them to livestock who are pinned in confinement situations, and we use our fields to capture their manure after we spread it. In a managed grazing situation, these livestock are out on the pasture in the fields most of the time. They go into milk once or twice a day, maybe 3 times a day in a really high production situation. But they're out there grazing, feeding themselves essentially, and spreading their own manure and their own excreta in a very distributed and diffuse way. Now, a key part of a managed grazing system is that the farmer spends his or her time managing where these livestock are grazing. And so we call it managed grazing because it's a very carefully controlled grazing situation. Unmanaged grazing, sometimes called continuous grazing, the livestock are just turned out into big open areas and allowed to graze wherever they want. And that has some very undesirable effects on the plant community. We're not going to go into that today. If you want to learn more about that, you can take a class called Grassland Ecology that I teach. Okay, let's move up to these cash grain systems. Continuous corn is grown as CS1. So this is year after year after year we plant corn. It's managed as a conventional system with a lot of herbicides to kill off the weeds. And we use a conservation tillage approach, which is to say that we only till in zones in and among the corn plants. Then we have a corn-soybean grain rotation, which is a year of corn, a year of soybean, a year of corn, a year of soybean. And that system gets minimum tillage, but it does get some tillage. Tillage, just to be explicit, is disturbance of the soil usually to maintain weeds, to control weeds, I should say, and also to sometimes to break up the soil clods, to break up the aggregates on purpose, because when we break up those aggregates, it makes a microbial frenzy in the soil. The microbes spill their guts, which is to say they put their nutrients that are in their bodies out into the soil, and then the plants can take it up. We've talked about that in previous talks. Okay, finally, our CS3, our Cropping Systems 3, is a corn, soybean, clover rotation, and there's a wheat cover crop that's planted at the end of the soybean harvest in the fall. That wheat crop grows over winter, and then it's harvested in the spring, and then we plant clover. This is an organically managed system. Okay, so again, no chemical inputs allowed. We can only use mechanical means of managing weeds. Now that's the topic for the day. These plant-plant interactions are immensely difficult to deal with in organically managed systems. And so while we are reducing the amount of chemical industrial herbicides that we spray on the fields to control weeds in these conventional systems, there's a trade-off, and that trade-off is that we highly disturb the soil over and over and over throughout the season to try and manage weeds. And so just to give you a sense for why that's important, I want to look at some results from our long-term cropping systems experiment. So this is just picking out a couple of treatments to compare. Cropping Systems 2, which is our conventional corn-soybean rotation, and then Cropping Systems 3, which is our organic corn, soybean, wheat. These yields are just soybean yields from the various soybean phases of those cropping systems. Here's the Arlington data and the Lakeland data. And what I want you to see is that these data are in bushels per acre. In corn, 40 bushels equals a ton of corn. Bushels is an old English unit. I'll show you here what a bushel looks like. Come back. Here is the standard bushel, which I think is somewhere in England. And you can see that it's roughly 8 gallons. And so that thing full of corn is a bushel. So 160 of those in a conventional corn, soybean system. I think I misspoke earlier and said these were soybean yields. These are actually corn yields as depicted here at the top. It's the corn yields from the corn phase of the system. Okay, So what's important to compare here are the conventional yields compared to the organic yields. Now, these comparisons are comparing broken down by wet springs. So of all the 29 years of data that we've had, this is looking at those years that had very wet springs where May and June rainfall was greater than 10 inches. Compared to normal springs, which are, when we had our normal rainfall, which is about 9 inches. So just rainfall in May and June. And this is a critical time because this is when weeds are getting established. And when the weeds get established, they become very hard to control. So the establishment approach is critical early on in the season. And so you can see that when it's very wet, we get a big reduction in corn yields compared to the conventional system, as compared to a normal spring when our corn yields are about the same. So here in normal seasons, we get about 95%. Our organic system is about 95% as productive as the conventional system. But in these wet springs, when we can't manage weeds, the eventual subsequent harvest is only about 75%, only about 3/4 of the conventional system. So this is just to give you some sort of sense for the importance of weeds, plant-plant interactions in agricultural systems. We've got to get those weeds controlled. And I'm going to post just a quick video then to show you how we do that weed control in organic systems.